Hi, I'm Martin Swetman, and in this video I'll continue my review of the Younger Dryas impact debate research. So far we've covered the published research from the original Firestone et al. Paper in 2007 through to the middle of 2018 in the last video, using the new bibliography at the Cosmic Tusk website. Now we're nearing the end of this review. There's only 2 years of papers left to review. Hooray! And what we found is that it's absolutely clear that a massive cosmic impact happened nearly 13,000 years ago. That times very closely with the onset of the Younger Dryas mini ice age and many megafaunal extinctions and human population bottlenecks and changes in culture. But establishing the likely mechanism for these changes and whether they were truly caused or triggered by the impact is always going to be harder to establish. Looking again at the new bibliography, we're left with just these 2 papers by Walbach et al. From 2018. But I'll also review the responses to these papers in 2020. So first there's the critical response from, well, guess who, Vance Holliday and his skeptical colleagues, and then there is this counter response from the paper's authors. And that's all for this video. I'll only review those 4 papers. But because these papers are so long, stretching to over 80 pages in total in the main papers, plus 51 pages of appendices, I'll split this episode into 2 parts. So let's get started with the first paper from Walbach et al. In 2018. Actually, these are 2 more papers from the Comet Research Group. Their focus is on the soot and charcoal left over from this event in the ground, and on trying to establish just how much biomass was actually burned by the impact. Because if they can show that a vast amount of biomass was burned very suddenly, then it might explain, at least partially, how the Younger Dryas mini ice age and many of the other effects were triggered, since a vast cloud of smoke and soot could block the sun's light for a long time. In other words, a kind of nuclear winter effect is proposed. And we've seen the same kind of idea used recently in a paper that caught the media's attention about how the dinosaurs were wiped out 66 million years ago. Apparently, that is best explained by the same kind of nuclear winter effect, this time caused by the Chicxulub asteroid rather than, say, atmospheric dusting caused by a massive volcanism that occurred at around the same time, at least geologically speaking. Anyway, back to the Walbach papers. Now, the first paper of this pair focuses on evidence in the world's ice sheets, while the second paper focuses on soils and sediments. And in fact, the first paper is split into 2 halves. The first half examines evidence mainly from Greenland ice sheets, while the second half provides more details on the likely cause of the impact, which is essentially the decaying comet that produced the Taurid meteor stream. Now, we've seen much of the evidence before in this first paper in one form or another in various places, but here it's collected together and clarified, which is useful because it's not entirely novel. So I'll try to stick to the main novel points in this first paper. So the first new data presented is here in this plot. So this is another look at the GISP-2 ice core from Greenland. And here we see the platinum trace on a logarithmic scale this time. And here we see the sum of the signals from different kinds of salt ions. And you can see that the platinum signal has this little pre-peak here with the asterisk before the main peak. And you can see that the timing of this platinum pre-peak coincides very well with a marked increase in these salt ions in the ice, which indicates a change in climate. So presumably we have much more stormy weather, or at least stronger winds at least over this period. And the dashed line is a fit to this data. So once again we can see the platinum and the climate change signals very closely coincide, meaning it's likely the impact caused the climate change. But what is really interesting about this is that the initial onset of the climate change, just about here, seems to coincide with the little platinum pre-peak and not the main platinum peak here. And as this data is from the same ice core, the GISP2 ice core, we don't need to worry about any potential misalignment of the data. So how can that be? How can the small platinum pre-peak have triggered the Younger Dryas climate change? Well, I'm not sure. Perhaps it means there were two impacts roughly 10 years apart. Maybe the largest impactors were captured into an unstable orbit around Earth for 10 years before they hit. Or, perhaps more likely, the platinum signal is undersampled, and really the initial platinum peak was higher. Anyway, I really don't know what this means, but it's an interesting detail that deserves an explanation. The next data we see is really a clarification of the data from the 2014 paper by Peteyev that discovered the platinum anomaly in the Greenland ice. So let's quickly go back to that paper and have a look at that data again. Now see how in this paper the ammonium signal here was placed around 30 years too late compared to the platinum signal, assuming they're related, of course. Now this caused several years of confusion and has been used to deny there was any large impact at all. Remember, the ammonium spike here is assumed to indicate extensive wildfires. But remember also, this discrepancy was actually caused by a typo in the 1993 paper by Mayevsky, from where all the ammonium data was obtained. And actually the platinum and ammonium signals coincide very well if you correct that typo. Well, back to the Wallbach paper. In this plot, that inconsistency is corrected. And we can now clearly see, using this more detailed data from the GISP2 ice core, that the ammonium signal and the platinum signals do in fact coincide very closely. Again, this is a trend line placed through the ammonium signal, and this grey bar here indicates the duration of the platinum signal. Probably these multiple peaks in the ammonium signal are caused by storms dumping ammonium-laden dust onto Greenland, and presumably this dust is still abundant in the environment. And probably the main ammonium peak, due to direct fallout from the atmosphere, has been undersampled. So it's nice that this discrepancy has finally been cleared up. Now here we have similar data from the N-grip ice core, also in Greenland. And so it's useful to make sure these two ice cores, GISP2 and N-grip, both agree. And so here again we have pretty much the same kind of data. We have the ammonium signal in the N-grip ice core fitted again by a dashed trend line. And here we have the oxygen isotope ratio signal, which is indicating temperature and climate at this position in Greenland. And we can again see that changes in the climate and temperature correspond very well to the changes in the ammonium, and with the timing of the platinum from the GISP2 ice core. Now, in this particular plot, the GISP2 and N-grip ice core data have been passed through a wiggle matching exercise and calibrated to a radiocarbon chronology, so we can expect them to line up fairly well, but not quite perfectly at every data point, and that's exactly what we see. And here we have data from yet another ice core, this time the GRIP ice core, that shows how other combustion products, so here we have the ammonium, but here we have acetate, oxalate and formate, So these are other kinds of combustion products, and they also have peaks at around the same time at the onset of the Younger Dryas period. Although this data has much lower resolution and is therefore less useful, nevertheless, the timing with the platinum peak in the GISP2 ice core, which is indicated by the vertical dotted or dashed line, is very good. And yet again, this time from an ice core in, well, this one is in the Antarctic and this one is in Siberia, we have other kinds of combustion product. These are now referring to, these are traces for nitrates. And again, they seem to show peaks at about the same time, although there's a little bit of misalignment with the GISP2 platinum signal. So this is pretty good, indicating that the entire globe probably experienced the effects of biomass burning, at least in terms of atmospheric pollution. And now we're looking at the change in atmospheric concentration of carbon dioxide. And this is from the Taylor Glacier ice core in Antarctica. And we can see that there is this sudden, almost vertical upturn in the concentration of CO2 in the atmosphere, what appears to be the Younger Dryas onset, which again is indicated by this dashed vertical line. That's the platinum signal in the GISP2 ice core. Although, again, it's hard to know exactly how this ice core record is aligned with the GISP2 ice core. And following that, we see that there is this dip and then recovery in the isotopic oxygen ratio of the atmosphere. Now, what do these traces indicate? Well, it's hard to be sure, but they could be consistent with large amounts of burning biomass, which would generate a lot of carbon dioxide and therefore potentially a change in the carbon isotope ratio. So the combination of all this data from the world's ice cores shows it's very likely an unusual burning event took place right at the onset of the Younger Dryas climate change, very close to the platinum peak in the GISP2 ice core. Now, a frequent counter-argument against this burning being induced by the impact is that perhaps a swift change back to ice age conditions might by itself cause increased biomass burning, since the environment would be much drier when it gets much colder. So it's not entirely clear that the increased biomass burning actually indicates a cosmic impact. It might not. But that's what the second paper from Wolbach et al. Tries to establish, and we'll go through the details of that second paper later. There might even be a combination of factors, the impact and climate change, that are hard to disentangle. Anyway, the rest of this first paper explains how such an impact might have been caused. Essentially, this is Kluber-Napier's giant disintegrating comet scenario known as coherent catastrophism. So now, here, we are looking at some orbital calculations for one of the largest known centaurs, which are comets that currently orbit between Jupiter and Neptune. And it shows that if we calculate Chiron's orbit forward in time for a few 100,000 years, we expect, or Chiron is expected to become a hazard to Earth, otherwise known as Earth crossing, several times in that time frame. And that for a period of around 8,000 years here, it will become trapped within an Earth-crossing orbit in the inner solar system. And given Chiron's size, which is probably in the region of 100 to 200 kilometers in diameter, it would be expected to be hazardous at this time. So what we're looking at here, these two different traces, so here we have a very long time scale result, and here we are zooming in to this smaller region on this plot. What we're looking at with these two traces here is the semi-major axis, that's this grey line, and the perihelion, or the closest distance to the Sun, of Chiron's simulated orbit over time. So that when these lines bracket this grey band here, then by definition Chiron has become Earth crossing. So in other words, it crosses Earth's orbit. Now we don't expect them to actually collide, because Earth and Chiron can be anywhere on their orbits at this time during this Earth crossing period. But at least there is in this interval the risk of a collision. However, the risk is very low. The problem for Earth then is not caused by a direct impact with Chiron, which would be so huge it would be a total disaster. No, instead, because Chiron is now orbiting within the inner solar system, according to the simulation at least, it would begin to degas and decay, producing hundreds, thousands, and even millions of large fragments. And it's because of the large number of large fragments that would be expected as Chiron decays that there is this realistic risk of a large impact. So this is how the Younger Dryas impact can be explained. The arguments presented here suggest that an impact on the scale of the Younger Dryas impact is reasonably probable if a centaur like Chiron attains an Earth-crossing orbit for a significant period, say 10,000 years. And given that Chiron is not alone, there are thousands of centaurs beyond Jupiter, most of which are relatively small, but a few are even larger than Chiron, and any of them could potentially attain an Earth-crossing orbit in the future and shower us with their decaying fragments within the next few 100,000 years, then an impact like the one proposed is entirely reasonable and even expected. In fact, given the known population of centaurs, this is the greatest impact hazard for Earth, greater than all the known asteroids in near-Earth orbits that NASA is currently focused on. Okay, so that more or less closes out paper 1. Now, rather than heading straight into paper 2 from Walbach et al., which focuses on quantifying the amount of biomass burning and its likely effects on the environment, let's instead see what the response is from Holliday et al. Regarding the new data from paper 1. So here is their paper, and we can see the usual names here of Vance Holliday and Andrew Scott, joined by Patrick Bartlein and Jennifer Marlon, who are both paleoclimatologists. Jennifer, like Andrew Scott, specialises in understanding the effects of climate change on wildfires. Now, their response is very lengthy, stretching to 26 pages of detailed comments. But if you can stay awake as you read through all this, you'll see that most of their comments don't actually address the new work at all. Instead, their paper is largely a long list of complaints about earlier papers by the Comet Research Group, papers that we've already reviewed, which means we've already addressed many of these comments. So rather than going piecemeal through all their complaints again, I'm instead going to focus only on the new points they raise concerning the new data from the first Walbach paper we just looked at. In fact, you have to wade through half of their paper here before you get to the one and only complaint about the data we reviewed from Walbach paper 1, which is here on page 15. Essentially, what they're suggesting here is that the data in the two figures that we looked at from Walbach paper 1 have been misaligned. First, they suggest that the GISP2 ammonium data is misaligned by about 10 years, which they show by replotting the data and comparing with the original data from Walbach et al. On this plot. So if I just zoom in, you can see that the red and black lines are separated by about 10 years. Well, even if this is true, it's a fairly trivial error. It doesn't really change much about the conclusions. We'll see what the counter response from the Comet Research Group is in a minute. And they say the same error is made for the ammonium signal in the N-grip ice core. Again, the black and red lines are separated by about 10 years. However, they claim that the oxygen isotope signals from this ice core, that's the blue and the grey lines, are about 60 years out. In other words, when they replot the data, their data is shifted by about 60 years compared to the original data plotted in Walbach. Now, if this is true, this would be a more serious error. So what do the Comet Research Group have to say about this in their counter response? Well, essentially, they stick to their guns by saying the mistake is due to a misunderstanding by Holliday et al. On the age scales used. So they point out that the lead author of that publication is a co-author on this contribution. In other words, if we look at the authors of this counter-response and the authors of the Walbach et al. Papers, we find that Paul Mayevsky is a member of the Comet Research Group. Now, Paul Mayevsky is heads up one of the world's leading research institutes into ice cores and interpreting their data. And so he was actually author of the GISP2 ammonium data. So if there's anyone that knows how that data should be aligned, then it's him. Well, I think that sorts out that. However, Holliday et al. Do point out one error that Walbach et al. Don't contest, and it relates to these plots that show the ammonium ion concentration in the GISP2 and down here in the N-grip ice cores over very long timescales, hundreds of thousands or 100,000 years. Now in these cases, the black line is the Walbach et al.'s data that they plotted, and the red lines are Holliday's et al.'s, which are from the original data file, which can be found on the internet. And it's clear that Walbach et al. Have smoothed the plot somewhat compared to the original data. Well, okay, so Walbach et al. Didn't mention that smoothing, so that must go down as a mistake. But as these plots are not central to their argument, which is why I didn't show them to you before, I don't think this jeopardizes the main thrust of their work or their conclusions. Okay, that's it for Walbach et al.'s first paper. Essentially, they are saying here in the first paper that the ice core evidence shows that the Younger Dryas climate change, the platinum signal, and indicators of biomass burning are practically simultaneous within the resolution of the ice core data available. And an event like the Younger Dryas impact is expected based on astronomical observations of the Centaur population of comets and the Taurid meteor stream. And it seems Holliday et al. Have no answer to this. Not only do they not dispute the new data that I reviewed, but they also offer no credible alternative explanation for it, other than it's all a coincidence. Now, it certainly is possible that it's all a coincidence. Maybe the Younger Dryas climate change caused a burst in wildfires by itself, and maybe the timing of the platinum signal indicating a cosmic impact is a coincidence. But statistically, that's unlikely. And moreover, the impact scenario explains all the other data too, like the nanodiamonds and impact spherules at the base of the black mat, which Vance Holliday et al. Refused to accept, even though all this evidence has been reproduced by several independent research groups. And we can expect extensive wildfires if a massive cosmic impact occurred, so it makes perfect sense. Actually, that's not quite an accurate portrayal of their position. I think Holliday et al.'s position is that even if there are some impact indicators at the base of the black mat, they are not coincident across all the different sites and have got nothing to do with climate change, megafaunal extinctions, or population changes. The problem for them here, I think, is that there is only one platinum spike in the Greenland ice core near the onset of the Younger Dryas period, and only one platinum abundance spike at the base of the black mat at each black mat site. There aren't multiple platinum spikes separated by hundreds of years, for example. And it's broadly the same for the nanodiamond evidence too. The only contrary evidence in terms of nanodiamonds is from Holliday et al.'s blind test the previous year, which in my view is a highly suspect piece of work and should be repeated. And while they dispute the nanodiamond evidence, they have no answer to the platinum abundances, because these are such relatively easy measurements to make and they're easily interpreted. So the platinum signal is really very important, as it clearly shows beyond reasonable doubt a single massive impact event occurred. It has no realistic alternative explanation. And you see, Holliday et al. Tend to avoid discussing this. In fact, they hardly discuss it at all in this highly critical paper. In fact, the only reference to the platinum data is here in their list of complaints. They suggest there are multiple platinum peaks found at the various black mass sites investigated by Moore et al. In 2017. Well, let's just remind ourselves of that platinum data. Okay, so here is the paper by Moore et al. Here is their platinum data. As you can see, there are a few other clear peaks in the data which might correspond to example for other cosmic impacts or volcanic eruptions. So we've got a little peak here, maybe a little peak there, and then at some of the other sites there are a couple of peaks here. This is probably just noise. We have a single peak. This is just noise, again noise, and maybe that's just a small peak there. So there are a few other smaller peaks, but none of them are within several thousand years of the main Younger Dryas platinum signal, except for this one at Arlington Canyon. But we know at Arlington Canyon this entire sediment sequence is practically the same age within the radiocarbon dating uncertainty. And it's also the only site with multiple nanodiamond layers of Younger Dryas age too. So very likely these multiple Younger Dryas age peaks in platinum and nanodiamonds at Arlington Canyon are caused by landslides or storms or other kinds of reworking and weathering in this canyon. So there probably was just one massive impact near the onset of the Younger Dryas mini ice age, although higher resolution plots of the platinum abundance would be desirable just to make sure. So to my mind, Vance, Holliday and colleagues are simply in denial. Their viewpoint seems to be incompatible with the evidence. It's as though they are blinded by some kind of belief that the impact theory must be wrong. Okay, so that's it for this part. I'll continue with the second wall back paper and the response and counter response in the next part.